Hi, and welcome to holiday lesson 4, the twins paradox. Having spent 3 holiday lessons in quantum mechanics, I thought we'd move over to special relativity. Today's lesson isn't on the A-level, but it's also not on the A-level. There are a couple of ideas here which you should be au fait with, and this I think is just going to bring them out and make them a bit more explicit. The twins paradox works like this. By this point, you should know that time dilates when you move the clock. Or to put it another way, moving clocks run slow. And the closer to the speed of light you get, the more time dilates. Because it's a speed squared divided by c squared denominator, you're not going to notice it at speeds less than about half the speed of light, and even then it's going to be quite narrow. So in our day-to-day life, we don't notice time dilation. However, when we go to really fast speeds, we do. And the faster you go, the slower times goes in that reference frame. Okay? Now the important thing to remember is time is always relative. We always describe this: if you look at your own watch, it will always look normal regardless of how fast you're going. All that ever changes is how quickly time flows for you relative to people moving at a different speed. The problem starts to come when we really start to drill into what that means, because we need to be very, very careful not to define absolute motion. And this could be tricky if we were not careful. And the twins paradox and the solution people provide to the twins paradox, I think, give us a really good insight into where the problems lie. So, we already know the following thing is true. If you take some people and you put them on a rocket ship and you fly them somewhere and then they fly back, less time will pass for them than it will if you'd remained on Earth. They did this on the Apollo missions. They got 2 very accurate atomic clocks. They synced them up, they sent one of them to the moon and back, and by the time it got back it was a full second behind the one that stayed on Earth, because time had dilated by a second. So therefore, if those people had hit themselves on the head every second for the entire time they'd been on their rocket ship, and the people on Earth had done the same, the people on the rocket ship would have done it one whole time less by the time they got back, because their clocks went slow because they were moving. We also see this effect in satellites. They're bombing around the Earth so quickly, they actually need to take into effect relativistic things in order they stay synchronized with clocks on Earth. And even really, really fast airplanes have to do it to a tiny, tiny degree. We've tested this endlessly, we're sure it happens. The twins paradox works like this. Imagine there are 2 twins. A twin here, who is in a rocket ship, and a twin who remains on Earth. The twin in the rocket ship accelerates at, say, 0.9 the speed of light, away from Earth for a very long time, turns around and flies back to Earth. We would expect this twin to now be much younger than this twin, even if they were the same age when this trip started, because time will have dilated hugely for this twin and not for this twin. So far, so hunky-dory. The paradox comes in here, because this twin can just say, but whoa, I stayed in the same place, and the Earth flew away from me and then flew back. Why is it that I'm young and you're old? Surely you should be young and I should be old. What is it about my motion that is different from yours? Hence, the paradox. The first and simplest way to answer this one, I really like, which is to say, well, remember when you got in that rocket, yeah? And you remember they had to turn the engines on, you experienced a massive force and you accelerated. Yeah, that would indicate that you're the accelerating one and this one isn't, right? At a very fundamental level, you kind of did get in a rocket and there was and you accelerated away from Earth, and that's kind of nuts, right? So therefore, expect that something weird happened to you and not to me. So at brute level, probably not a problem. But there are some more sophisticated solutions, which are kind of groovy. One of my favourites works like this. We can imagine that every month, the person on Earth sends a message to the rocket ship, so that there are, moving through space at any time, messages going out from Earth 1 month apart. If you think about it, as you were flying away from Earth, you'd actually get the messages at a slightly slower rate than they were being sent out, because you'd be moving with the messages. What we're seeing here is a sort of Doppler shift type effect. And then when you stopped and turned round and started heading back to Earth, you suddenly start getting the messages at a faster rate. So some people say, well, maybe this should tell us that time dilation might happen more on the way back than on the way out. Maybe they're not the same. But that doesn't make sense, because surely the speed of light is the same in all directions, and the universe is homogeneous, and whether I'm flying away from you or flying towards you, we'd get the same amount of time dilation. But that might not be the case. And the reason for that is something so absolutely wacky that I'm going to have to preface this by saying, this is really wacky and out there. It is true, doesn't matter, but it's interesting. That is the one-way speed of light. It works like this. Imagine you want to measure the speed of light. You stand here and you get out a torch and you shine it forward and you bounce it off a mirror and it bounces back and you see how long it took to get here and then get back on your stopwatch. Hunky-dory, you know the distance, you know the time, you measure the speed of light, not a problem. However, you assume that the light took the same amount of time to get from here to here as it did to get from here to here. So now you think to yourself, well, how do I know that is the case? How do I know that the light took the same amount of time moving left to right as it did from moving right to left? I've just assumed that. So you think, well, what I'll do is, right, I'll just measure it this way, and then I'll get my mate to here, and they're going to wait till the thing gets to them, and then when it arrives at them, they'll stop their watch, and then we'll see how long it took there. And okay, great, no problem, we solved the problem. But then this person's going to have to move here so you can compare watches. And the moment you do that, you've got a moving watch, and it's going to dilate. So that doesn't work. So then you think, well, what if this person, when they get the message, sends a signal back? Well, that signal is also going to be made of light. So that's going to move at the speed of light, and so therefore that sort of bakes in as well. You can't move the clocks because they'll dilate, and you can't send a signal because all signals will move at light speed. So it turns out that you can never actually measure the speed of light in one direction. All you can ever measure is a so-called two-directional speed of light, the time it takes to go somewhere and come back. You can never actually find out if it took the same amount of time moving away from you as it did moving towards you. The universe will conspire to stop that from happening, which is weird. And it means that for all we know, there might be no time dilation at all on the way out. It might all happen on the way back. And in fact, that, if you think about it really carefully, would be okay. Because as long as the rocket never gets back to Earth, or starts getting closer to Earth again, it never needs to find out if the time dilation happened. It's only when the two twins meet up that we'll find out if the time dilation was real. So it might be that the speed of light in this direction is infinite, and this direction is half the speed of light. Because if you think about it, that would give you the speed of light overall. Meaning that if you were moving this way, you'd have no time dilation, and this way you'd have double time dilation. And that would still all work out fine, because when the twins got back together, you'd get the amount of time dilation you'd expect. Weird, right? Really, really weird. So, at a very basic level, twins paradox is solved by you were in a massive rocket ship and I wasn't. This is not a problem. At a much more complicated level, what some physicists believe it is when you turn around and decide to come back, that is when the time dilation starts to get locked in. It is only by the action of moving away and coming back that we ever really time dilate. And that if one were just to fly away from Earth, you might time dilate, you might not, but we'd never actually know. So there you go. Enjoy the end of Easter holiday. I'll see you next week.